Stars are in equilibrium under the action of forces. Outline how this equilibrium is achieved. Can you tell me? The reason for the balance, the equilibrium of a star maintaining its size like our sun right now without contracting.
Because there's the gravitational force that is pushing the layer in, but there's like the forces from the fusion reaction that pushes like the core outwards. So those two forces balance
Exactly.
each other.
Yeah, exactly. Okay, answer to that, 1816. The photon, the fusion, radiation, the pressure, or the forces caused by that nuclear fusion generate an outward forces, outward pressure, which balance out the gravitational attraction. The nuclear fusions reaction, fusion reactions produce an outward pressure or outward forces which balance the gravitational attractions of matter in the sun, keeping it, maintaining its equilibrium. Attraction. Okay. Main sequence star P is 1.3 times the mass of the sun. Calculate the luminosity of this star relative to the sun. Which equations among these do we use to answer this question? Luminosity and the mass. Knowing the mass of a star is 1.3 times the mass of our sun.
Can we use the second one from topic D2?
Yeah, here is one. Yeah, D2, second one here. Luminosity proportional to the power 3.5 of the mass. So we can write it as follow. The luminosity of that star P compared to the luminosity of our sun is the mass of that star P to the power 3.5 compared to the mass of the sun power 3.5. We need to know calculate luminosity P relative to the sun, meaning we need to calculate this thing, the ratio relative to the sun, meaning we need to calculate the ratio, not the value of the luminosity singly, meaning specific value, but this ratio. Okay, it simply means 1.3, the ratio of the mass to the power 3.5. Okay, it is only 1 mark. Yeah, 1.3 power 3.5 is 2.5. It is 2.5 times more luminous compared to the sun.
Okay.
Equivalent to 2.5 sun. Okay, the next one. The following data apply to gap crust, radius, temperature, distance, luminosity of the sun is 3.85 times 10 to 26. Determine the luminosity of gap crust relative to the sun. You said 19 April, meaning we have 2 more weeks.
Yep.
Yeah, 2 more weeks to review for paper 3. But we need to spend some time for the math also, not only paper 3.
Yeah, okay.
We return to like the normal schedule next week. 2 days, 2 sessions a week for math and 2 sessions for physics.
Wouldn't 19 April be like 3 more weeks? Because 19 April is like the middle of April.
Yeah. 3 more weeks. Yeah. So we just return to the normal your schedule, with math. Yeah. And up to now, I think you have some basic knowledge and practice with this paper.
Okay.
Which you just need to practice a little bit more with the session A, huh? For session B, I think that we have some basic, huh? Not too
Okay.
scary like before, like when we start learning.
Yep.
Yeah. Get cross. The velocity of the sun determines the luminosity of gas crust related to the sun. Radius, temperature, distance, given luminosity of the sun. Okay. Look at these quantity, the given things. Which equation do you think we can use? Temperature.
There's like the middle, like the second equation, D1. Also
D1,
luminous.
the luminosity area and powerful temperature. Powerful temperature. But area, we don't know the area of this gas crust star.
But then we have the radius.
Distance. Oh, radius, yeah. Having the radius, we can determine the area. Temperature, powerful, and sigma. Okay. Do that calculation here and take a screenshot and put it here on the board. Or you can write directly on the board.
Yep.
Let me take a screenshot of the paper here also. Page 1. I'll erase the other page.
All right.
Pages.
Do you need to find a ratio here because it is asking relative to the sun?
Luminosity gas rate. Yeah. Do the ratio. Calculate that thing and then divide the luminosity of the sun given the 3.85. Yeah.
Yeah, I think got the ratio.
Yeah. Ratio 265. The answer is like double that. Okay, let me check if there's something wrong with the calculation. Powerful the temperature. The radius. 4 times 4 pi square is the formula for the area of the sphere. 4 pi r square, area of the sphere. Okay. You forgot the value for.
Okay, let me try again.
Sphere area. Is that 10 to the negative 8 for the Stephen Boltzmann constant?
Got the answer.
Okay, yeah. You round it to 2 significant. Distance 2 or 3. I think if we can take 3. We can take 3.
Sure, it's 3.
If this luminosity given 3 even figure, also radius. But the temperature is 2. Do they accept 3? Only write 2. I think it's because of the temperature. You only take 2 figure for the temperature.
Okay.
Okay, the next question here on the next page. The Hertzsprung raster diagram shown. A diagram through the main sequence. An S letter, huh? Please draw on it. A band, an S letter band. Curve a little bit like this. There.
Okay.
A pretty wide band, not a very narrow line, huh?
Yep.
Plot the position using letter P for the main sequence star. You calculate it in B. Oh, I didn't. Okay, B here. Luminosity main sequence star. A band. You need to know draw another line. Yeah, making a band in the main sequence.
Got it.
Oh, here they give very wide band. Question 2 down here. Position a letter P, the main sequence star you calculate in P is in B, meaning the luminosity is only 2.5 times compared to the sun.
Yep.
And the temperature, do we know it? No. 2.5 times luminosity, which is very close here. Wait. 2.5 here, like here, huh? And then what about the temperature? Somewhere here.
That's 3,600 because it's given.
Temperature? No, this is another star, the gas crust star. The star
Oh.
in part B, the star P, another one. So we only know that it is a star on the main sequence, and its luminosity is 1.3, 1.5 times
Okay.
compared to Sun, huh? Which is here. 2 to 2.5, 2.5 times here, huh? And then you draw a line, horizontal line to this. It could be somewhere here on the main sequence, just to the middle, huh? Okay.
Okay.
See the position of the star P, which is different from the Gakrus.
No. Okay.
Gakrus. Plot the position letter G for Gakrus. The temperature of Gakrus is 3,600, somewhere between 5,000 and 2,500. Is that like right in the middle? 3,600. 2,500 divided by 2 plus 2,500. Yeah, almost in the middle of here, huh? To 3,600, almost in the middle. And the luminosity you calculated 1,100 times more luminous than the sun, which is here. Here, Gakrus, huh?
Yeah.
So it is supposed to be a red giant. That is the next question. The next one. Discuss with reference to the change in mass the evolution of star P from the main sequence until its final stable phase. The star P will keep burning, fusing the hydrogen and helium, and then that amount of hydrogen run out, not enough to produce enough outward pressure to balance the gravitational attraction. The star collapse, reduce the size, and then the particle accelerate more, increasing the temperature. When they attract each other, decreasing the size of the star, huh? And that temperature, the new high temperature, is high enough, the particle move fast enough to restart the nuclear fusion. And now nuclear fusion is even stronger than before, making the outer layer expand, becoming a red giant.
Okay.
And then that red giant, until the final state, that red giant can explode. If the star is very massive, such as 10 times more massive than the sun, the explosion of a red giant can be a supernova.
Right. Let's type in
Star evolution. I will put another picture to illustrate that. 3 different endings of a star. Yeah. And according to the mass scheme, where is the answer of that? Okay. The Gakrus, which is 1,000 times more luminous than the sun. Wait, the star P. The star P is only 1.3 times more massive than the sun. 1.3 is lower than the charge crescent limit, 1.4, huh? Times the mass of the sun. So, the star will become a equilibrium white dwarf. It will not explode. Okay, its final ending is a white dwarf. Dwarf. Okay. So please describe that.
Okay.
3 marks for 3 ideas. Huh? The main sequence star to jet giant, it will evolve, it will collapse first, and then expand, becoming a red giant, and then the outer layer explode, forming a planetary nebula.
Right.
The core keep contracting and cooling, becoming a white dwarf. Actually, the temperature of the white dwarf is even higher than the temperature of the red giant. The white dwarf is located at the bottom left corner of the HR diagram, having greater temperature than the red giant. Deplete hydrogen source, contract, restart the nuclear fusion, explode the outer layer, forming planetary nebula. Let me search for the picture of the closed nebula. Closed nebula to the Earth, like a neighboring exploded star. Helix nebula. Helix means closed. Oh, it looks like an eye.
Yeah.
It will end up being white dwarf. See the closest nebula to our Earth, and how far is that? 700 light years. It is Sauron eye. Helix nebula closest, and 700 light years away. I haven't seen the complete of the writing. And again, if the temperature of this nebula is not high enough, but below a limit, which there's an equation for that limit, which is not in the syllabus, so sorry, not in the data booklet. So it's not very likely to be given in a test. If the temperature is not high enough, then the nebula will contract, and after a few million years, it will form a new star. Wow, a lot of writing. Once the outer layer will contract, which increases the temperature further and reignites the fusion reaction again. This would expand the outer layer of the star even more, returning to a red giant when the fusion reaction stops. Now, it does not stop, it's just too much and then explode. The outer layer will become, the outer layer, after explosion, the outer layer become a nebula, a cloud in the space, mostly hydrogen, like 90, 70 at least, or 90% hydrogen, and a little bit of helium. Okay, the outer layer will become a nebula, a cloud in space, and the core contracts, becoming a white dwarf. Here, the first branch on the tree here.